modulo P, which is a prime. If it is not prime, then there can be many more solutions than just n. But if it is prime, then there are at most n solutions. For instance, assume that we relax the condition. This P, so condition, assume that P is not prime. So this is the end of the theorem. If P is not prime, then there can be more solutions. For instance, I want to find the solution to this kind of equation. Mod 8. So 8 is not prime, right? 8 is not prime. Then, for instance, 1 is a solution, right? And also 7 is a solution. By the Lagrange theorem, there should be 2 solutions. Is it true or not? It's not true. Why not? Because in the case, this should be prime, right? It should be prime. But I relax the condition using non-prime number, then suddenly it's a second order equation, but there are more than 2 solutions. Why? 3 is satisfied. 3 squared is 9. 9 is congruent to 1 mod 8, so it is okay. Even 5 is okay. 5 squared is 25. 25 is congruent to 1 mod 8. In other words, if we do not require the mod condition with prime number, then as you can see, there are 4 solutions for the second order equation. Do you see it? So the key part here is prime P, and then nth order equation has at most n solutions. This is the key. But if we do not have the same situation using composite modulus, then it is violated, right? Even though it has second order equation, it has 4 incongruent solutions. Of course, we are mentioning about incongruent solutions. Assume that 1 is a solution, then P plus 1 is a solution, 2P plus 1 is a solution, and there are infinitely many solutions having these things. But if we just consider incongruent things, then 1 and P plus 1 are congruent, right? 1 and 2P plus 1 are congruent. 1 and any number times P plus 1 are congruent to 1, if we just consider congruent solutions, incongruent solutions. Then the next thing that I want to solve is, do is developing small corollary to the Lagrange theorem. And it says this, assume that we have a specific equation. Lagrange theorem is for general one. It's for pretty much general equation, right? It's for general equation. But assume that we have a specific equation like this. Mod P, the same mod P where P is prime. Then the equation, the corollary says, there are exactly the solutions. Exactly the solutions. When you have a equation of order D, then there are exactly the distinct solutions or the incongruent solutions. So this is the one that I will prove using Lagrange theorem. So let's do it. First of all, I will mention that the condition, and then if D divides P minus 1, right? If D divides P minus 1, P is a prime number, and then D divides P minus 1, then x to the power of D has exactly these solutions. So let's consider this for any a between 1 and p minus 1. So we pick a between 1 and p minus 1. Do you see? I pick any a between 1 and p minus 1. So there are a total p minus 1 possible a's, right? Then, so if we pick, if a is between 1 and p minus 1, then a to the power of p minus 1 is congruent to what? Do you see the 0 by what? Fermat's-Little theorem, right? Fermat's-Little theorem says if we take p minus 1 in the power position, then it is congruent to 1. Fermat's-Little theorem, right? We proved it before. Then, as you can see, because d divided p minus 1, we can say, oh, d times k is p minus 1. Do you see? d divided p minus 1 can be written in this form. d times k is p minus 1. In other words, a to the power of dk minus 1. And then we can rewrite it using a to the power of d minus 1, and then a to the power of d k minus 1, and then a to the power of d k minus 2, all the way down to a to the power of d, and then 1. So we can write the equality this way. So take a look. For this equation, I will count the solution with you. For this equation, how many solutions can you count? How many solutions between these can you count for this equation? How many? P minus 1 solutions, right? This equation is P minus 1 solutions. And by Lagrange theorem, this equation has d times k minus 1 solutions and most, right? Do you see? So it has definitely p minus 1 solutions, and this has at least d times this for solution, and then this is equal to dk minus d solutions, or dk is what? dk is p minus 1, right? p minus 1 plus d solutions. So take a look. This has p minus 1 solutions, and then this is equal to product of these two. But this has at most these many solutions, right? That means this has how many solutions? This has how many solutions? At least these solutions, right? At least, because of this situation, this has at least these solutions. If you don't understand this reasoning, ask me. It has p minus 1 solutions between 1 and p minus 1, right? So if we count the number of integers between these, is p minus 1 solutions. And then by Lagrange theorem, this equation has these many solutions, right? These many solutions. And most, right? And most. Then this should have at least these solutions, right? Why? Because if we add these two, it should reach p minus 1. To reach p minus 1, the only way is adding these things together to get, I made a mistake right here, it's minus. It is minus. Right? So to reach this thing, we should add this thing to reach p minus 1, right? So it has at most this solution. That means it has at least these solutions. But this order equation had at most how many? At most these solutions. By Lagrange theorem, right? By Lagrange theorem, this has, by the way, this order equation has at most these solutions by Lagrange, right? By Lagrange theorem, right? So it has at least these solutions, and most these solutions, meaning what? It has exactly these solutions. So this is the end of the problem. So please check whether you completely follow this approach or not. If you don't, ask me. So this is the end of the proof, and I'll continue unless you stop me. So assume that d divides p minus 1, then x to the power of d minus 1 has exactly d zeros, right? So as you can see, x to the power of d minus 1 has exactly these zeros when d divides p minus 1. Why? By Lagrange, it has at least, this portion has at most these many solutions, and by PERMA it has p minus 1 solutions, so something squeezed in between, right? The number of solutions here should satisfy both conditions, right? P minus 1 solution part here, at least this part solution. That means it has at most this part of solution, meaning it has at least these solutions. But by Lagrange applied to this portion itself, it has at most these solutions. So this means this has exactly these solutions. So we completely proved this theorem. So x to the power of d minus 1 has exactly these solutions. But is it always true? Is this always the case, even if we relax the condition? So assume that we relax the condition. In other words, I said d should divide p minus 1. But assume that we do not include this kind of condition. Then what may happen? So for instance, let's not worry about the relaxed situation now. Later, when we cover for the final, for the second exam, we will consider. Then final theorem that I will prove before the second exam is this one. It is theorem 8.6. Theorem 8.6 says if P is prime, right? P is prime, and D divides P minus 1, then there are exactly phi of D incongruent integers having order D mod P. So this is the final statement that we will prove before the exam. So let's begin. So we add, so let's represent n of d. Let's use the function n of d represent the number of just a moment, integers having order d. So this is the definition. The n of d represents the number of integers having order d mod p, right? Mod p is assumed. I do not repeat it, but mod p is assumed. For instance, n of 5 means what? Number of integers having order 5, right? Then we add these things for possible d's. D should divide p minus 1, right? D should divide p minus 1. So, for instance, D1 divides p minus 1, D2 divides p minus 1, and then J divides p minus 1, and so on, and then D something divides p minus. So all these are divisors of p minus 1. Then we add all of these things. We add all of these things. Oh, number of integers having order D1. And then number of integers having order D2. And then the number of integers having order D something. To be more specific, I will use sigma notation. I am adding all divisors of p minus 1, right? Or the number of integers having order something, right? Order something which is a divisor of p minus 1. So I am adding these things. Then, as you can see, how many can you find in this approach? There are total, how many? P minus 1, right? By Fermat's-Little theorem, it is P minus 1. Right? So initially it has order here, order here, order here. The maximum possible order is P minus 1. So something has P minus 1, something has less. But in any case, by Fermat's-Little theorem, a to the power P minus 1 is 1. So you cannot exceed it, right? So the number 1 through P minus 1, total P minus 1 integers. So the same reasoning as before, but if you don't understand these things, ask me. So we are adding the number of integers having D1, D2, and so on up to D something, right? As you can see, by the theorem that we proved before, every number between 1 and P minus 1 satisfy this thing by Fermat's-Little theorem. Do you see it? Right? In other words, the order of these elements should satisfy what? Should divide this, right? The order of these elements should divide this. In other words, the order of these things cannot be different than these groups, right? So we create this thing, and it should be P minus 1. Then what is the strategy? The strategy is this. We want to show that this number of elements having D is nothing but phi of D. So this is the, we want to show, right? We want to show, right? We want to show this fact. In other words, the number of integers having order D is nothing but phi of D under that condition. So we have this situation. If we add n of D for the possible divisors, for all possible divisors, then if we add all these integers from 1 through P minus 1, then there are total P minus 1 numbers. But by the theorem that we proved before, for any n, the addition of phi of D for any n is what? This number, right? We proved this thing before using multiplicity, right? Because P is multiplicative, we can add these things for just prime power. For the prime power, we get the prime power. We proved this before. So we can replace this box by any number. We can replace this box by P minus 1, then it is P minus 1. But it is not just bound to P minus 1. It could be any number. Or any number is possible. So take a look. If we add, they are equal. N of D, if we add N of D, and then phi of D, they are equal. So what you want to show is, under this condition, getting this one, right? So we want to show this fact. The other direction is trivial. If n of d is phi of d, then sum is the same. The other direction is trivial. But we want to go reverse. So what is the situation that we want to avoid? We want to avoid this kind of situation. Oh, n of d and phi of d are sketched, right? N of d, this is the graph of n of d. Assume that this is n of d, and this is the phi of d. Then they are not equal, right? If n of d looks like this, phi of d looks like this, they are not equal, right? They are not equal. So what we want to show is this one. Oh, can phi of d always greater than or equal to n of d? So that is the one that I want to show. In other words, assume that phi of d is always greater than or equal to n of d everywhere in the domain. Then the only way possible is what? They are equal. Because if there is any strict difference, then under this condition, there is no chance to catch up. N of d cannot catch up phi of d. If somewhere phi of d is strictly greater than n of d has no chance to catch up. But they are still, the sum is still the same. Is it possible? No. So once we prove that this happens to all d, then we are done. Why? Because the sum is equal. In the end, the sum is equal, but n of d doesn't exceed phi of d. Then that means what? They are equal all the way through. In other words, if somewhere and phi of d is strictly greater, then the only to compensate is going down. But it is strictly greater than, it is always greater than or equal to n of d. Phi is always greater than, right? Or equal to. So it cannot happen. In other words, once there is a strict difference, then it's impossible to catch up. N of d cannot catch up. So once I prove this thing, then it means n of d is in fact the same as phi of d, which is the desired result that we claimed here, right? So you should know the strategy first before going into or jumping into the proof. But if you don't understand strategy, ask me. So the goal is showing that the number of elements, right, number of integers is equal to phi of d. So this is the goal. To prove it, what you do is some equality, right? Some are equal. Then are the functions or summand equal? That is a claim. And I will show that it is equal. Why? Because n of d doesn't exceed, n of d doesn't exceed the phi of d, right? N of d doesn't exceed the phi of d. Why? Because n of d doesn't exceed the phi of d, then they are equal at each point. If somewhere there is a strict difference, then n of d has no chance to catch up under this condition. So I explained more than enough and even repeated many times. Now I will begin unless you stop. So let's do it. So we are focusing on n of d. Assume that, so given d, right, which is a divisor, right, which is a divisor of p minus 1. If n of d is 0, then done. Why? Because 0 is less than or equal to phi of d, right? Phi of d is greater than or equal to 1, right? So if n of d is less than or equal to phi is equal to 0, then we are done. Do you follow me? So n of d equals 0 is a trivial case. So let's not worry about this trivial case. Let's worry about non-trivial case. In other words, this case is done if n of d is greater than 0. In other words, there is at least one element having order d. Then we have some element, say A. So there exists there is an A. There is just A. Let's say A. There is A. having order D, because you said this thing, right? In other words, number of integers having order D is greater than 0. So I say, oh, let's call that element A. In other words, A having order D. So if you don't understand, you can ask me. Why? Because n of D is greater than 0. Number of elements having order D is greater than 0. Then we call that element A, at least one element there, A. Then what is the strategy? Oh, with A, I can form a incongruent number up to D. In other words, oh, A to the power of 1, A to the power of D, 2, A to the power of 3, all the way up to A to the power of D. So we consider D numbers. Then these are all possible incongruent numbers, right? These are all possible incongruent numbers satisfying the condition. Any questions? So these are all possible. We proved similar things before. Then let's go to the next page. So before jumping to the next page, I will let you know the strategy. Among these D numbers, when you consider order D, how many will have order D? Usually, this kind of order is determined by D over GCD, right? Right? I will go to the next. So this is a little bit strange. Without explanations, I will go to the next page and explain. So we have D incongruent numbers. Satisfying right? By Fermat-Lederer theorem, A to the power of D is 1, right? So we have these incongruent numbers because of the order, right? Order is D, right? A order is D, any K. So K running from 1 to D, right? Then we have A to the power of 1, A to the power of 2, and then this is it. There are not any more numbers than these numbers in this system, right? If you don't understand, ask. Then among these things, consider A to the power of K. Then what is the order of A to the power of K? Order of A to the power of K is what? D over GCD, right? D over GCD of D and K. I proved this before, right? So many small things that we proved before are claimed and used. So take a look. To have order D here, something here may have denominator greater than 1. Then D over denominator greater than 1 cannot be D. In other words, something will be disqualified, right? So what will be qualified? Only when denominator equals what? 1, right? So it's not disqualified, or just qualified if GCD of dk is 1. In other words, if you have greater than GCD, then order will become smaller than D. Then it is disqualified in our consideration of n of D, right? N of D only counts the order D, not less than n D. So among these D numbers, how many, among these incongruent numbers, how many has GCD equal to 1? By the definition, phi of D numbers, right? Right? So there are, by definition, right? There are phi of D numbers having this condition, right? So we are done, right? Because we have proved that there are, at most, phi of D numbers, n of D is less than or equal to phi of D. Any questions? So this is the end of the story, and I already mentioned that this is enough to prove the equality, because sum is the same. Each term is smaller or equal, less than or equal, right? Each term is less than or equal, but the sum is the same. The only way to catch up is always equal. Anywhere it's strictly smaller, then there is no chance to catch up. Like you are trailing like 3 points. Each time the opponent points 3, then points something, then I point the same number, then there is no way to like catch up, right? Always the strictly greater than this number counts, right? Then we cannot catch up. Impossible. The only way possible is always the same, right? Always matching point by point. That's the only way. So this is the proof. So we completely proved this thing. And as a corollary to this, is not, I'm not proving it. I'm just stating the corollary. And the corollary says this thing. If P is prime, then there are exactly phi of P minus 1 primitive roots. Of P. So this is the reason why we were proving many things. Why? Because phi of P minus 1 is nothing but this thing. Take a look. D is a divisor. D is a divisor of P minus. I wrote down that thing before. So I will go back to the previous theorem that I proved. If D divides P minus 1, then n of D is, phi of D was the one that I proved, right? The number of elements having order D is phi of D. That was the one that he proved, right? Then now, pick specific D. If D is equal to P minus 1, right? P minus 1 divides itself, right? P minus 1. Then what happens? The number of elements having order D minus 1, the number of elements having order D minus 1 as P of D minus 1. Sorry. P minus 1. So the number of elements having order P minus 1 is P minus 1. And the number of elements having P, the number satisfying, the number having order P minus 1 is called primitive root, right? Any number having the order P minus 1 is called the primitive root by definition. So the number of primitive root, so I will write down the verbatim translation. The number of integers having the order P minus 1, right? It's called n of P minus 1. Do you see? It's verbatim translation. The number of integers having order, given here, order D, or P minus 1, is given by n. That number is this one. But now, by definition, integers having order P minus 1 is called primitive root, right? Because it's plural here, I will use plural. So primitive roots. In other words, the number of primitive roots, right? The number of primitive roots is n of P minus 1 happen to be phi of P minus 1. So this is the end of the proof. So I completely proved all the way up to this one. And as I mentioned before, in summary, I gave this last time, but in summary, I will write it one more time, unless you have a question. So the summary of this chapter is this. I gave it last time. Primitive root, the number of primitive root, right? The number of primitive roots can be counted if it exists, right? If it exists. If it doesn't exist, automatically 0, right? Because it doesn't exist. There are two possible cases. It does not exist. There are two possible cases. The primitive root exists, or primitive root may not exist. Then when does it exist? If p equals 2, 4, p to the power of something, or 2 times p to the power of something where p is odd, right? P is odd prime. So in these cases, primitive root exists. But in other cases, primitive does not exist. In other words, the number of primitive is 0. Then in this case, how many primitive roots? How many primitive roots? Then it is phi of p. Assume that p is prime, then phi of p is what? P minus 1. Assume that p is not prime, then we need to calculate, right? In any case, we know the number of primitive roots. So sometimes instead of using p, people use n, right? People use n. It is a little bit awkward. I said p and then pp here, so it's a little bit awkward. So I will write it using n. But n can be prime, right? If n is prime, then phi of p is p is p minus 1, and phi of p minus 1 is the number of primitive. So before going to the review for the exam, I will ask a question. Oh, I have a number p. Then how many primitive roots can you count? How many? It is what? Phi of 13, right? And then phi of 13 is what? 12. Right? Phi of 12 is what? 12 multiplied by 1 minus 1 half, 1 minus 1 third, right? Do we have any prime factors than 2 and 3? There are no other than 2 and 3, so this is it. So 12 multiplied by 1 half multiplied by 2 thirds, then there are total 4 primitive roots. In other words, when we have p equal to 13, then there we can find 4 numbers having, we will find 4 incongruent numbers having this mod 13, right? So this, but it doesn't happen before 12, right? It doesn't happen before 12. So let's check it. I says 13. So let's run our program to do it. It is 13, and then I'm running it from 1 to 13, and then I will do it. So when a is equal to 2, what happens? When a is equal to 2, as you can see, power 1 gives us 2, power 2 gives us 4, power 3 gives us 8, 4 gives us 3, 5, 6, 7, 8, 9, 10, 11, 12. So 12's power is the smallest power achieving it. Do you see? So this means the number A, in this case 2, is what? A primitive root, right? So for 13, then we can find the 2, right? And then next number that I want to use 3. So let's use 3. So I use the 3. If I use 3, then first power gives the 3, right? 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 1. So it is disqualified, right? 3 is disqualified. Do you see? 3 disqualified. 4. But it's not even prime, right? 4 is not even prime. 5. So I used 5. Then first is 5, second is 12, and then third is 8, and then fourth is 1. So 5 is disqualified. 6 is not even prime. 7. So if I use 7, then what? 7, second power, third power, fourth power, fifth power, sixth power, seventh, eighth, ninth, 10th, 11th, and then 12th. 12th is the smallest power achieving it. In other words, 7 is qualified. Do you see? 7 is qualified. And then 8 is not even prime. 9. So let's check. In fact, we don't have to limit ourselves to just primes. Even non-primes can achieve primitive root. So I skipped something, but I felt it is not a smart idea to skip them. At least check them. 2, and then as you can see, it reaches this, so 4 is disqualified. And then one number I skipped, 6. Then let's run it. 6. And then 6. 6 is okay, right? As you can see, 6 is okay. So even if it's not prime, 6 itself is not prime, it doesn't matter. Any number satisfying the order condition is called primitive root. So 6 is a primitive root. Do you see? 6 multiplied one time, twice, 3, 4, 5, 6, 7, 8, 9. And then 12 is the first time, so 6 is qualified, right? So I mistakenly tried to get rid of the composite numbers, but it's not necessary. 6, 7, 8, 8. Let's use 8. Then what happens? 8, 12, no, disqualified. Do you see? Fourth power gives us this thing. And then 9. Then as you can see, even 6th power or earlier power, right? Even earlier power gives it, so disqualified. 10. As you can see, 10. Then it is achieved earlier, so it's disqualified. 11. And as you can see, it is not achieved before, right? 11. Only time it occurs is 12th power, so 11. So I found total 4 primitive roots. In other words, phi of 13 is the number of primitive roots, and then phi of 12, and then 4, right? There are total 4 numbers satisfying the condition, primitive root condition. So we cannot find the primitive root easily in straightforward calculation, but at least we can count the number of primitive roots using the theorem. Any questions? Then now from this point on until before the exam, I will review for the exam, and you can ask any questions about the exam related thing. First of all, I am not covering the review systematically, intentionally, because I will begin the systematic coverage from Wednesday. But today I will cover something that could be very important. First thing that you need to know is cancellation law. Cancellation was mentioned and used at least 20 times in proofs or in calculations, and you should know the cancellation law. Assume that we have AX equals AB, mod anything, right? Mod P. Then I want to cancel out A. But what you should avoid is this kind of calculation. Oh, is this correct or not? It's not correct with the same mod. It's not correct. Cancellation law says if we cancel out A, then we must divide this mod by GCD of A and P, right? GCD of A and P, right? So this is called the cancellation law, and you should know this clearly. Then using this, we can solve this kind of problem. Oh, solve this. Right. I usually use just a G, and then GCD, G equals the GCD of A and P. Then I usually use this kind of. So you may make a problem. For instance, what problem? Oh, like 4 times x equals 12 mod 24. So assume that you have this kind of problem. Then how can you solve it? How can you find all the solutions? The key is what? Cancellation law. You see 4 and 4. So I can cancel out 4. So I can cancel out 4, then I can say 3. Is this correct? It's not enough. Why? Why not? Because we need mod 24 divided by G. G happens to be 4. Right? G happens to be 4. Then because of this, the solution is this. X should be congruent 3 mod 6. Then what kind of things are solutions? Oh, 3, and then 9, and then 15, and then 21, and then 27, but 27 is congruent to 3 mod. So if we use the given mod, right? Given modulus, right? Given mod 24. All of these are different. Here, same, right? With mod 6, 3 is congruent to 9, is congruent to 6, 15, and 21. All of these are congruent in mod 6, but with mod 24, 3 and 9 are not congruent, right? So with mod 6, it is this one, and using this, we get these numbers. Then these are the numbers that you can find, right? So let's use these numbers here. If you use 3, what happens? 12 is congruent to 12. Done, right? Done. If you use 9, then 4 times 9 equals what? 36. And then if you subtract 24, 36 o'clock is 12 o'clock, right? So the same, right? Done. 15, then 4 times 15 is 60. 60 minus 48 hours is 12, right? So 12, the same, right? As you can see. And then 21, 4 times 21 equals 84. 84 o'clock is equal to, if you subtract to 72, then it is 12 o'clock, right? In other words, we solve the problem by using cancellation rule, right? By cancellation rule, we find the result, and then we translate this result using the given modulus 24 instead of 6. So do you clearly see the way to use cancellation rule or not? So you should be very careful. If I see this kind of statement on the exam, then I cannot give you full credit or even give much point because, oh, I solved it by canceling out 4 and then I got 3. And then you say mod 24. Then at best, you can get like 1/4, right, or 25% of the points. But in addition to this, the penalty, you do not use cancellation rule, the penalty, right? So at most, like 20% you can get if you write just 3. Do you follow me? If you write just 3, then you will get only 20% of the scores for that problem. Right? 20% only. But if you use cancellation law correctly and then state these things, then you get full credit. But the key point is cancellation law.
That's really two parts of the problem. Is this cancellation law just gets you to the point where you can find x equals 3, and then the other theorem or property is how many possible solutions.
Yeah, that's true. Yeah. You can regard them as two parts, but you can regard these parts as just intuitive part. In other words, solution should be 3 mod 6. Then 3 mod 6 are these kinds of numbers going on. And among these things, what are incongruent with mod 24? Then we should consider up to mod 24, then a total 4 numbers. So you can regard this as theorem part, regard this portion as theorem part, but it can be just called intuitive, right? Intuition part. Any other questions? So cancellation law is very, very useful and important. And even in this case, as I mentioned before, when you have equality, we can multiply, divide both sides by the same numbers and so on, right? But when you have congruence, we want to divide, right? We want to divide by some number. Then, unlike equality, we cannot use the same modulus. Do you see? Same moduli. Right? If we want to just divide. So when you do multiplication, division, and all sorts of things, you should be extremely careful to track down possible thing. But very basic thing. Assume that they are congruent mod 100. Then are they congruent mod 10? So if this happens, is this true or not? From big mod to small mod, is it possible or not? Or not? It's possible, right? But what about the other direction? What about the other direction? If this happens, then can this happen? Just pick some example, like 1 and 11 are congruent with 1 and 11, but 1 and 11 are not congruent with mod 100. Right? So when you cannot track down appropriate property, then you can pick your own example, right? 1 and 11 satisfy this, but doesn't satisfy this. So you should be very careful when you multiply, divide, or change mod, right? Big to small direction is always okay. But if you want to do the other way, then you should be very careful. And you may ask questions instead of systematically covering all the way from like chapter 4. You may ask questions 4 through 8, right? We spent about a month for the exam 1. We spent more than almost 7 weeks for exam 2. So about 3 chapters covered, and then 4 through 8, like 5 chapters are covered in this. So you may ask questions. Excuse me? I see. Chinese remainder theorem says this. Assume that x has some number a1 mod n1, and then if it has a2 mod n2, and so on, right? So assume that you have the condition that all these numbers are relatively prime. All of these numbers are relatively prime. Then Chinese remainder theorem says, oh, then x is congruent to some number mod product of these numbers n1, n2, all the way up to n. This is called the Chinese remainder theorem. And then also it states the method of finding this number. Method of finding this number. And where do we use Chinese remainder theorem will be briefly mentioned. Unless you have a question about the statement itself. The theorem itself. First of all, you can make up any kind of problem. Oh, I want to find consecutive numbers. So this is used in any consecutive number. Right? Find consecutive number satisfying your condition. Right? For instance, first number, say A is divided by, for instance, A is divided by something to the power of 5. And then the next number, A plus 1 is divided by something to the power of 10. Right? And the next thing, A plus 2 is divided by something to the power of 100. And then, I will use bigger power. So A plus the next number is divided by something to the power of 1 million. So assume that you are asked to find this kind of thing, then automatically you can convert these things into the Chinese remainder theorem. So let's do it. So I will call A using unknown x, right? So x is congruent to 0 mod something squared, right? Something to the fifth, right? Mod. And then x is congruent to -1, right? This equals 0 means this is -1. Mod something to the power of 10. And then x is congruent to -2. Mod something to the power of 100. And then x is congruent to -3 mod something to the power of 1 million, right? Do you see it? Then the only condition that we need to impose is the relatively prime moduli condition, right? Relatively prime moduli condition. So you may pick, for instance, I will pick 2 here. I may pick 3 here. I may pick 5 here. I may pick 7 here, right? Do you see? Do you see? Then it's a Chinese remainder theorem application problem. Then you can solve Chinese remainder. You can solve this problem using Chinese remainder theorem and find the number x satisfying this. So for instance, I did some calculation. So take a look. Problem 7b has this thing. Obtain 3 consecutive integers, right? 3 consecutive integers satisfying this one. First one is divisible by a square. Any number square, like 5 square, 2 square, any number square, right? Second is divisible by a cube, any number cube. And then third is divisible by 4th power. So for instance, you may pick, 2 to the 4th power. You may pick 3 to the cubic power, right? And you may pick 5 squared, right? Then by bearing possible numbers here, like instead of 2 to the power of 4, you may pick 7 to the power of 4, or 8 to the power, 9 to the power, 11 to the power of 4, and so on. You may find these kind of numbers. There are infinitely many numbers satisfying this condition. Then you may think, oh, it happened because only 3 consecutive problems. No. You can find 1 trillion consecutive numbers, right? In other words, first number is divisible by a square, right? Second number is divisible by a cube, and then 1 trillion and first number, and 1 trillionth number is divisible by like 1 trillion and first power. That kind of thing is also solved by Chinese remainder theorem, and there are infinitely many numbers satisfying these things. Do you understand the situation, or if you don't, you can re-ask.
We're going to go through the practice test
On Wednesday and Monday.
and then practice test
Practice test is all extracted from textbook. So I will answer questions, because if you don't have enough time, then you can return back to the text to find them. So read these things and then ask questions if you don't know. That is the efficient way, instead of going through 1 and then 2 and then finishing everything at this, and then we cannot cover the other things. Do you follow me? So you read these things and check whether you follow or not, and then you can ask, then I can answer it.
Do they all have solutions involved?
Yes, all solutions in the book.
Some of them are problems.
Yes, problems in the
Yeah,
book,
so
right.
we don't have the solution that you want.
Solutions,
Unless you do it again.
if you see that page, then you can find the solution. For instance, that's the reason why you ask questions. If you ask questions, then I can answer, and then I can find the solution with you. Like, if you look at these positions, then you can find the solution. These are the solutions.
But like on set A number 3,
Set A number 3,
yeah, that's like one of the homework problems.
yeah.
Yeah, so
So assume that you see, then I will go to page 77, and as you can see,
yeah, it's page 75, number 25,
I see.
number 3. So that's like number
I see. I see.
I know how to
In this case, I proved it in class. It's in the note. Right? Because it's in the note, I will point the note. But if you ask, so you can ask any questions.
So no more new stuff.
Excuse me.
No more new stuff until after the test.
After the test means what?
We're not going to have
No,
the
just-
material until after we take the test.
Right.
Oh, I see. That's true. That's true. That's true. After the second exam is done, then we will cover more things for the final. But before that time, we will cover no more new material. Just these things we will focus on, and then you may ask any questions on these things. But after the second exam, I think, as you can see, we will need to cover after the.
Or is it a third test?
It is a cumulative. In other words, I will cover 9, 12, 13, right? And then 15 through 16 are optional. In other words, if you are fast enough, we may cover some problems, but roughly 9 through 13 will be added to 1 through 8 on the final exam. But in any case, before jumping into problem sessions or systematic review session, if you have any question about any part of these 5 chapters, ask. Because I announced that I will begin to review from Wednesday. Some people might want to come from Wednesday, but if I begin to review, then they might be upset, right? So please ask questions that you want to know now, and then from Wednesday I will systematically cover the review part. Before you find some questions, I will tell you about this kind of thing. Oh, prove that something is divisible by, for instance, something, right? So these are the things that you need to answer. Then what should you do? You should say that, oh, this kind of statement, right, or some statement, right, some statement is congruent to 0 with this. So this is the technique that you need to use, right? In other words, divisible should be converted to equations, right, equal to 0 with mod. This is the technique you need to use. So one interesting thing, with mod 9, 10 is congruent to what? 1. Right? Then if I can square the left side, then 100, right? 100, and I can square the right side 1. In other words, any appearance of this kind of thing is congruent to 1. So with mod 9, we can easily prove something is divisible by 9. So I will mention the things that we will need in the future. Open for. So this thing, a prove that 1, 2, 3 is divisible by 9. Of course, when the number is short, you may really do the long division. But on the exam, you may have longer one. Then what should you do? Oh, 1, 2, 3 is congruent to 1,000 is congruent to 1, right? And then 2,000 is 2 times 1, right? 200, right? And then 30 is congruent to 3 times 1, and then 3 is congruent to 3. Then, if you add these things, 9. And the 9 is 0, mod 9. Thus, 1, 2, 3 is divisible by 9. So please check these things and ask questions. Check the statement. In other words, to prove something is divisible, you do not really have to divide. And like I can make up any problem, right? So prove that this is divisible by 9 or not, right? Either way, right? Then instead of really dividing it, you should use the theorem. Do you follow me or not?
You can do these for the remainder problems too. What is the remainder of
Right. What is the remainder? Right. Things like it. Right. And then the next thing is 11. With mod 11, 10 is congruent to what? -1, right? With mod 11, 10 is congruent to -1. Then $100 is congruent to what? 1. And then 1,000, -1. So it alternates, right? Negative, positive, negative, right? Negative, positive, negative, positive, negative, positive. Then using these properties, we can prove that something is divisible by 11 or not. So let's make up. Is this divisible by 11? The only thing that you need to do is checking the even or odd position, and then add the even position and then odd position, and if the sum is equal, then they are 0. So I used 1, 3, 2, 2. I can make this as long as like, right? As long as I like, right? As you can see, 4, 5, 6, 7, and then I can add this position and add these position, and then adjust in the next position, right? So it's 1, 3, 4, 6, 14, right? And then now the other position is 2 plus 2 plus 5 plus 7. Then as you can see, it is 12 and then 16. So if we have difference 2 in the next step, it will work, right? Right? Difference 2. So this will be divisible by 11. So let's check it using MATLAB. 1, 2, 3, 2, 4, 5, 6, 2, 4, 5, 6, 7, 9, 7. 7, 9, 7 divided by 11. As you can see, it works, right? So I can make up any problem. If this is a computation course, then I may write like 100-digit number and then ask you to check whether it is divisible by 11. Some students may say, oh, we don't have enough time. Some people may think, oh, I can solve it within 10 minutes or less than 10 minutes. In any case, I showed you some nice property. In other words, divisible can be converted to congruent to 0 with that number, right? Divisible by something becomes this mod. So there are some properties that you can use. Any other questions? Then let's stop, and next time prepare some questions like, oh, you want this thing like that.